Our next Mythbusters, this actually, before we start, is the 100th Mythbuster. So, hang on. So, this, I have a lot of you know that I have a list of topics that I kind of accumulate over the years. And this was actually one of the first things I put on the list because I've been teaching this for probably more than 30 years. But no one has ever had the gumption or the wherewithal to actually take this topic on until now. And I was really impressed. So Dr. Tiffany Vanderlip is going to be talking about something that I was taught, some of you may have been taught, is the bicarbonate on the blood gas as good as the bicarbonate on the chemistry panel. One is calculated on the blood gas versus the one measured on the chemistry panel. Dr. Vanderlip.
I'm just going to start by apologizing to anybody who thought they were done hearing about the Henderson-Hasselbalch equation. So again, my myth is that calculated bicarb on an ABG is not as accurate as bicarb measured on a chem panel and should not be used. So we use ABGs all the time. They're really important in assessing a patient's acid-base status for metabolic and respiratory disturbances. Bicarb is the main extracellular buffer, and it does 75% of the total buffering. So it can be either calculated from an ABG or measured on a chemistry panel. But as Dr. Freed was talking about, there has been a historical concern regarding the accuracy of this calculated bicarb from an ABG. I'll get into that quite a bit. So bicarb in the body has different forms, or CO2. So there's CO2 dissolved in plasma, bicarb, and carbamates as well. As far as calculation of bicarb, that's where we use the Henderson-Hasselbalch equation. I'm not really going to go too much into this, but the ABG machines use a derivative of the Henderson-Hasselbalch equation to measure the bicarb from to calculate the bicarb from the measured pH and PaCO2. Whereas the measured bicarbonate is not actually measured bicarbonate, it's actually total CO2. That plasma, strong gas is, I wrote strong gas, I meant strong acid is added to the plasma, and the amount of total CO2 that's released from the plasma is measured. And so that contains not only CO2, but also bicarb and the carbamates. So about 95% of that is bicarb, but not all of it. And so that venous total CO2 is usually about 2 to 3 millimoles per liter higher than the arterial bicarb, and that's not only from elimination of bicarb from the lungs, but also the inclusion of dissolved CO2 and carbamates in that value of total CO2. So here was a study of over 17,000 paired samples. This was comparing calculated bicarb from an ABG with measured bicarb. This is rather than measured total CO2. They found that 98.5% of these paired samples were within 3 millimoles per liter of each other, and the mean difference was 0.36 millimoles per liter. They also took 20 of those samples and introduced air bubbles of different amounts, and found less than 1 millimole per liter difference after introducing the air. Here's another study with 312 samples, 51 patients. These were all drawn from arterial lines, where the difference in total CO2 and that was measured and calculated bicarb was 0.8, and 95.3% of those samples had a difference of less than 2 millimoles per liter. And then again, you can see that the R squared for this is 0.9366, so highly correlated. Another sample, 89 paired samples, again showing strong correlation. This one, they separated the samples by the level of the bicarb, and they were trying to show that with a low bicarb being less than 20, that it was a little bit less strong of a correlation. But even then, they show that there was a significant difference between the means, but it was from 15 to 17, so still only 2 millimoles per liter. And the R squared was still 0.95. Here, another study, 56 patients, 63 paired samples, total. This one, the total CO2 was measured differently than how we measure it. We measure using enzymes. They were measuring using ion-specific electrodes, but again showed a strong correlation between the total CO2 and the calculated bicarb. You can see the correlation coefficient of 0.987 and mean of difference of only 1.5. I have a table here just showing some sources of error for these values. So for pH and PCO2, they can both be affected by temperature, so patient not being normothermic, but they also note delay in analysis for PCO2, but we usually are drawing an ABG and immediately analyzing it, so I don't think that really applies. And for bicarb, I'll get into this a little bit later too, but the other values, the pH and PCO2 being abnormal, can affect the bicarb calculation because you're using the Henderson-Hasselbalch to calculate it, and and a lot of articles warn that if you have an error in one of those, the error in the bicarb measurement, because it's a logarithmic equation, the bicarb could be a lot higher, but we'll get into that in a few minutes. And then what I really wanted to show you here was that the total CO2 can be increased when there's a delay in analysis. And that can happen very easily. There's a lot of patients who have blood drawn, it goes to the lab and can sit there. There can be delays. So I think it's very easy for that one to happen. Here is another study. This is looking at the actual machine that we have, our ABG machine, the Chem Premier 5000, and its quality control. It has this continuous quality control rather than intermittent quality control. So it was comparing this continuous quality control to doing quality control every 6 to 8 hours, either manually or automatically. And it was able to detect errors that the intermittent quality control couldn't. And the precision for every data point, or all of the measurements, including pH and PCO2, were all over 6 sigma. So very precise. This is a measurement of total error, so the maximum amount of ABG the maximum amount the ABG measurements could be off from the gold standard value. And this is minimal for the pH at just 0.04. For the PaCO2, it's the total error is a little bit higher at 5 millimeters mercury and up to 8%, which would be, for a PaCO2 of 100, it would be 8 millimeters mercury. This is showing the R squared, comparing the Chem analyzer, which we have, to the reference analyzer, which is almost perfect at 0.998 for both the pH and PCO2. So that's showing that the Chem analyzer is very accurate in measuring both the pH and PCO2. Here you can see the range of values the machine will accurately measure and output. It's a very wide range, and then below the table are the values of PCO2 in millimeters mercury rather than kilopascals. So that range would be 6 to 150 millimeters mercury. So as I mentioned before, a lot of articles were warning that if the ABG measurement of pH or PCO2 were incorrect, that the error in the bicarb calculation would be magnified because of the logarithmic equation in the logarithmic function in the Henderson-Hasselbalch equation. And this really appears to be an exaggeration with the accuracy of the technology. And this is a test of that with some extreme values for pH and PaCO2. And this is assuming an error of 8 millimeters mercury either way. And the differences with the calculated bicarb in these examples is it ranged from 0.8 to 2.4. And that's well within the range of error for the measured total CO2 values on the chemistry panel. In summary, when drawn concurrently, the calculated bicarb is very strongly correlated to the measured total CO2 drawn. These aren't often drawn concurrently, and the acid-base status could change significantly during the period between these two being drawn. So that really should be taken into account, and as well as the ABGs are drawn and analyzed immediately, whereas, as I mentioned before, venous samples, there can be delays in the lab, temperature changes, there could be exposures to air and other sources of error. And the calculated bicarb also just more closely aligns, as I mentioned, with the acid-base status at the time of the measurement of that pH and PaCO2 rather than a total CO2 drawn at some other time.
Anybody have any comments or questions?
So based on what you read and what you found, I'm curious as to where you think this myth originated. Like, where did the question of whether the calculated bicarb on the gas come into question?
You probably don't have any thoughts on that, do you?
I'm
think
sure you do.
I don't know. This is short answer is I don't really know. I mean, I was taught that when I was a resident and fellow. Actually, when I did my fellowship, some of the other fellows and I actually did a mini study. We didn't publish it or anything, where we did this, and there was like no significant difference between the samples, between the chem lab and the blood gas. So I don't know where this came from. I think the concept was, oh, well, we're measuring one and we're calculating the other, so the measured has to be right. Well, first of all, we're not really measuring bicarb on the chem panel. We're measuring total CO2, which is different. It's 90%, so that's within 1 or 2 milliequivalents, which is basically the difference between in most of these studies between the blood gas and the. So I think they're probably even closer than it looks, but I don't. I don't know where it really started or how it started, and I think one of the things when I teach this, as you probably know, is that if you don't believe the calculated is as good as the measured chemistry panel, then you don't believe in algebra. Because if you have, an equation with 3 unknowns and 2 of them are known, you solve for the third one, it has to be correct. So the big thing is that people say, well, what if there's an error in the measurement of the pH or PCO2? Or what if there's an error in the measurement of the total CO2? And you can see there's a lot of things that will affect the measurement, and opening it to air for a long period of time will definitely change it, and they do that in the lab. So anyway, that's the long answer to your question. Any other thoughts or questions? All right, well, I guess it's time to vote. So the calculated bicarbonate on the ABG is not as accurate as the bicarbonate actually measured on the chem panel and should not be used for determining acid-base status. How many think this is now still true? How many think it's plausible? How many think this is just busted? We're not going to be looking at that anymore. I think it's busted, so why don't you just click that? As an extra special, since this was the 100th Mythbuster, we have I hope you've enjoyed the series. We'll be back in September with more myths.